Hello students, welcome back to the lecture series on discrete mathematics. We are learning binary relation and this is the video part 4. Here we are going to learn the types of the binary relation. Let us go to the first type, which is a reflexive relation. A relation R on a set A is said to be reflexive if A, A belongs to R for all A belongs to A, that is, all the members of the set A should be related to itself. Consider the following relation on a set A which contains 4 elements 1, 2, 3, 4. In the relation R1, we see that the order pairs 1, 1, 2, 2, 3, 3 and 4, 4 are there. So we say that 1 is related to 1, 2 is related to 2, 3 is related to 3 and 4 is related to 4. Since all the elements of the set A are related to itself, R1 is a reflexive relation. In the relation R2, we have the order pairs 1, 1, 2, 2 and 3, 3. Since 4 is not related to 4, the condition is not true for all the elements for the set A. Therefore, R2 is not a reflexive relation. R3, we have considered the Cartesian product of A cross A. Since A cross A contains all possible combinations or all possible order pairs, that will be a reflexive relation. In this example, number 1, we have considered is equal to on a set of real numbers. Since all numbers are equal to itself, this is an example of a reflexive relation. 2 equal to 2, 3 equal to 2, 3 equal to 3, since these are the numbers which are equal to themselves. Example number 2 is a subset of, is a reflexive relation on the set. Since we have seen the property that every subset is a subset of itself, and therefore this is also an example of reflexive relation. In the example number 3, we have is of the same height as for the set of people is a reflexive relation. For example, if you consider students in a particular class and if you take this relation that is of the same height, so each student is of the same height as himself. And therefore example 3 is also a reflexive relation. Since we know the matrix of the relation, in the remark we are saying that if R is a reflexive relation, then all the diagonal entries of MR are 1. Since the diagonal entries are of the type 1 row, first column, second row, second column, third row, third column, that means the element is related to itself. So therefore the diagonal entries will be 1. Now the next is symmetric relation. A relation R on a set A is symmetric if for any two members of the set A, if we have A related to B, then we should also have B related to A. That means if the order pair AB belongs to R, then we should also have BA in the relation R. Consider the following relation on set A which contains 1, 2, 3, 4. In R1 we have 1, 1, 1, 2, 2, 1, 3, 4 and 4, 3. We see that 1 is related to 2 and we also have 2 related to 1. 3 is related to 4. We also have 4 related to 3. Therefore, the relation is a symmetric relation. In the relation R2, we have the order pairs 2, 3, 3, 2 and 4, 2. 2 is related to 3, 3 is related to 2. But 4, 2 order pair is there. 4 is related to 2, but 2 is not related to 4 in the relation R2. Therefore, R2 will not be a symmetric relation. Let us see a few more examples. The example 1 is less than or equal to is an example of symmetric relation. Since equality is there, we can also say that 2 is less equal 3 or 3 less equal 4 or 4 is less equal 3. Since equality is there, we can say this and this is an example of symmetric relation. Is friend of on a set of people. For example, again you consider the number of students in a particular class. If A is a friend of B, if person 1 is friend of person B, we say that person B is also friend of person A. So this kind of relation is also a symmetric relation. Example number 3 is married to on set of people. If you have set of people not in the class, you consider any set of people. If a person is married to, if a man is married to another lady, then that lady is also married to the person. So that means this is also an example of symmetric relation. The remark is a symmetric relation on A, then the matrix of the relation is a symmetric matrix. That means the matrix MR and its transpose will be equal. Since we have both type of relation, A related to B and B related to A, the number of ones and zeros will be organized symmetrically. Next we have antisymmetric relation. A relation R on a set A is antisymmetric if whenever A is related to B and B is related to A, we should have A equal to B. That means in no case if A is related to B and B is related to A not equal to B, that will not be an antisymmetric relation. If you consider the relation less equal, if A is less equal B and B is less equal A, it always implies that A is equal to B, and therefore the relation is antisymmetric where we have A less equal B, B less equal A, and then A equal to B. Let us see a few more examples. Consider the following relation where we have 1, 1, 2, 2 and 3, 3. Even if the 3, 3 is not there, this will be an example of antisymmetric relation. Example 2 is divisor of is antisymmetric on a set of natural numbers or positive integers. Why? Because if A divides B and B divides A, this means that A is equal to B. Because we are not considering the negative numbers, so the possibility that 2 divides -2 and -2 divides 2 and both of them are not equal will not be considered here, since we have the only positive integers. Now next is the transitive relation. Transitive relation on a set A is said to be A is related to B, B related to C. This should imply that A is related to C. That is, if A comma B pair is there, B comma C pair is there, then A comma C should be there in the relation R. Consider the first less equal type of relation. We know that if a number is less equal another number and that number is less than the third number, automatically the first number is always less equal the third one. So the relation is transitive. In the example number 2, we have the order pairs 2, 3, 3, 2. 2 is related to 3, 3 is related to 2. So therefore, 2, 2 order pair should be there. But since 2, 2 is not there, R is not transitive. Let us see a few more examples. Strictly less than relation is also a transitive relation. If A is strictly less than B and B is strictly less than C, then A is strictly less than C. Same way, greater than relation is classmate of. If A is classmate of B, B is classmate of C, automatically they are of classmates of each other. Is divisor of. If A divides B and B divides A, that means A divides C. Is equivalent to, in case of if you are considering matrices or any relation, then if it's equivalent to is a transitive relation. If A is equivalent to B, B is equivalent to C, then A is also equivalent to C. In the next lecture, we will consider the equivalence relation